Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome to the 29th lecture of the course Discrete-time Markov chains and Poisson processes. So in the last lecture, we learned several properties of Poisson processes. So a Poisson process is a counting process which starts from 0. It has stationary independent increments and the number of events that occur in an interval 0 to t is Poisson distributed with parameter lambda t. Then you say that it is a Poisson process with parameter or with rate lambda. Fine. So, and then we saw that the interarrival times, which is basically, so Tn is called the nth interarrival time if it is the time between the occurrence of the nth event and n minus first event. So, we saw that these interarrival times are exponentially distributed with parameter lambda, and that gave us a corollary that the time of occurrence of the nth event has gamma n lambda distribution. Fine. And we also saw that Poisson process has this Markov property, or in other words, probabilistically it restarts itself at each point of time, which means that if you start observing a Poisson process from a point, then you can pretend that the Poisson process actually starts from that point, and you do not need to really know that when it actually started. So, in order to say things about future, you can very well pretend that the Poisson process started from that point itself. Fine. So, this property is called Markov property, and I also mentioned this, that this Poisson processes is one of the simplest example of a much wider class of stochastic processes, which is continuous time Markov chains. Fine. So, today we will continue with further properties of Poisson processes. So, let Nt be a Poisson process with rate lambda. Suppose that each time an event occurs, it is classified as either type 1 or a type 2 event. So, you are classifying events, or events are classified into two types, type 1 and type 2. Suppose further that each event is classified as type 1 event with probability p, or a type 2 event with probability 1 minus p independently of all other events. So, once an event happens, it is with probability p, it is classified as type 1, and with probability 1 minus p, it is classified as 1 minus as type 2. And again, this each time an event happens, you classify it independently of everything else. Fine. Okay. Now, let n1t and n2t denote respectively the number of type 1 and type 2 events occurring in the time interval 0 to t. Fine. Now, it is easy to see that Nt is basically n1t plus n2t, because Nt is counting the total number of arrivals, n1t is counting the arrivals of events of type 1, and n2t is counting the arrival of events of type 2, right, where each event is classified as type 1 with probability p and as type 2 with probability 1 minus p. So, now what is the theorem? The theorem says that This N1T and N2T are again both Poisson processes with respective rates lambda p and lambda times 1 minus p. Furthermore, the two processes are independent. You said like two processes are independent means like information about one process doesn't give you any extra information about the other process. Like for example, if I tell you the number of type 1 events that has arrived in the say time interval 0 to t is say k, then that doesn't give you any information about the number of type 2 events. Fine, that's roughly what independence means. So, if you classify each arriving event as type 1 and type 2 with probability p and 1 minus p respectively, and then you just count the number of type 1 events and number of type 2 events, then individually they are again Poisson processes, but now the rates are lambda p and lambda times 1 minus p, and you can see where this p and 1 minus p is coming from, because you classify an event as type 1 with probability p and an event as type 2 with probability 1 minus p. So, basically you can think of it as like there is a single arrival stream and then you break it into two parts. That is why this is called this Poisson thinning. So, you are kind of thinning or separating the arrival into the total arrivals into two groups. Fine. Like one real life example that you can think of is like suppose customers are arriving in a departmental store and then each arriving customer is a male customer with certain probability p and a female customer with certain probability 1 minus p. Fine, then the total number of male, so if the original arrival process was Poisson with rate lambda, then now the arrival of male customers will be Poisson with rate lambda p, and the arrival of female customers will be Poisson with rate lambda times 1 minus p, and these two processes will be independent, right. That is one real life way of thinking about this Poisson thinning. Fine, okay. So, now let us see an example of this concept of Poisson thinning. So, what does it say? Phone calls arrive at a call center according to a Poisson process with rate 10 per hour. Again, I mentioned this in previous lecture as well. The unit is important, like here the unit is per hour. Now, if each arriving call is a complaint with probability 3 by 5, so again here you are doing some kind of classification. So, a call that is coming to a call center will be a complaint call with probability 3 by 5 and something else with the remaining probability, but it will be a complaint call with probability 3 by 5. Then the question is, what is the probability that no complaints arrive between 10 to 10:30 a.m. So, calls are arriving according to a Poisson process with rate 10 per hour. Fine. Now, each arriving call is a complaint call with probability 3 by 5, and this is independent of all other calls, right. So, each arriving call is a complaint call with probability 3 by 5, and it can be some other kind of with some other issue or other type of call with the remaining probability, but we are not bothered about that for this particular problem. So, each arriving call is a complaint call with probability 3 by 5. Now, you are asked that what is the probability that there will be no complaint calls between 10 to 10:30 a.m. Fine. Now, how do you solve this problem using the concept that you learned in the previous slide, the concept of Poisson thinning? Now, using previous theorem, complaint calls arrive according to a Poisson process with rate. So, the original rate was 10. So, lambda is 10, and here what is p? P is 3 by 5. So, the rate of arrivals of this complaint calls is lambda times p, which is 10 times 3 by 5, which is equal to 6. So, using the previous theorem, we get that complaint calls arrive according to a Poisson process with rate 10 times 3 by 5, which is 6 per hour. Fine. So, this is what we get from the previous theorem. We said that if we look at this N1T, which is the counting the number of type 1 events. So, that is Poisson with lambda, Poisson with rate lambda times p. So, here you can think of type 1 as complaint calls. So, then it is a complaint call with probability 3 by 5. So, the complaint calls arrive according to a Poisson process with parameter 10 times 3 by 5, which is 6. Fine. Now, what you are asked? You are asked what is the probability that no complaints arrive between 10 to 10:30 a.m. Now, you know that this Poisson process has this property of stationary increment. So, if you want to say something about the number of events in a particular interval, then you only need to know the length of the interval and not exactly where the interval is situated. So, that is what is stationary increments. We know that Poisson process has this property of stationary increments, which tells you that the number of events in a particular interval of time, in a particular time interval depends only on the length of the interval and not exactly where the interval is situated on the timeline. So, you are basically asked that what is the probability that in an interval, now see here unit is important, it was 10 per hour and here the duration is 30 minutes. So, this is basically in terms of hour, t is half, right. So, here the unit is hour, so 30 minutes is half. So, you are basically asked that what is the probability that there will be no arrival in a time interval of length half. So, what will be the required probability? It will be just e to the power minus so now the new arrival rate is 6. So, e to the power minus 6 by 2. So, this by 2 is coming because now the time unit is half, because the original time unit was hour and you are asked about a 30-minute window. So, the time unit is half. So, you get e to the power minus 6 by 2, which is e to the power minus 3, which is roughly like 0.05. So, it is a very small probability anyway. But the important thing is how we are using this theorem on Poisson thinning to solve this problem. So, each arriving call is a complaint call with probability 3 by 5. So, the complaint calls arrive according to a Poisson process with rate 10 times 3 by 5, which is 6. So, you are now asked what is the chance that in a 30 minutes duration there will be no complaint calls, but since the rate is in terms of hour, so 30 minutes is in terms of hour is just half. So, you are basically asked that what is the chance that there will be no arrival in a time period of length half, and that is just e to the power minus 6 by 2, which is e to the power minus 3. Fine. So, the problem is very simple if you understand this concept of Poisson thinning properly. Fine. Okay. So, we will end today's lecture here. Thank you all.